Hi, I'm Brian Green, coming to you now from Arizona State University, where we're having a conference on quantum mechanics. But since this has been a pretty special day from the point of view of discovery in physics, we figured we'd just answer some of your questions that have to do with the Higgs particle. And I've got my friend and colleague, Laurence Krauss, roped him in to join us to answer a few of those questions too. So I'm just going to turn to some of the questions that you've sent in to the website, and we'll just answer them back and forth, see how far we can get with that. So one question, which I think is a real good one, Laurence, is someone asks, there are other theories in physics that make use of fields that are very similar to the Higgs field, like inflationary cosmology makes use of a field called the inflaton field, but in actuality it's very similar in its properties to the Higgs field. So if today's discovery holds up, we don't know that it will, but assuming that it does, would it bolster your confidence in some of those other theories, in particular inflationary cosmology?
Yeah, that's a really good question, actually, because in some sense, we have no other example of a field like this, a fundamental scalar field that is uniform throughout space, as far as we can tell. It's a remarkable postulate, truly remarkable, and in some sense, this now indeed does give certainly me more confidence that such a thing is a possibility. Until then, there's been lots of examples of composite phenomena that look like this, but nothing fundamental like this. So it certainly bolsters my confidence.
Yeah, me too. I really feel pretty much the same way. Another question, which I think is one that naturally comes to mind, a viewer writes in, when I think of particles colliding in these huge machines, I envision the debris consisting of fragments of a size smaller than the original particles. So how can the Higgs have a mass 126 times that of a proton, since protons are the particles that are being slammed together? And the answer to that is that these machines don't just pulverize the particles into the pieces out of which they're made. What really happens is the machine takes the energy of the colliding particles and makes use of E equals mc squared, which tells us that energy is transmutable. It can transform from incarnating in one set of particles to another kind of particle. So the energy comes in, it becomes raw energy when the particles collide, and that energy can then reform into other particles. And if the incoming particles have enough energy, that means they can create particles of big mass. And that's how they can create a particle as heavy as the Higgs particle. And frankly, that's why the tunnel in Geneva, Switzerland is so big. You need a big tunnel so these particles can rev up to a fantastically high speed, getting enough energy to be able to create a particle, in this case, maybe the Higgs particle.
Yeah, the only thing I'd add is that that's, people sometimes think we build these big machines because we want to spend money, but in fact, there's just no other way to get that kind of energy, and that's what's required.
Yeah, exactly right. So let me grab one other of these questions. The Higgs field, the questioner asks, gives mass to fundamental particles like the electron, but what about massless particles like the photon? Are they somehow an exception? Do they stand outside the theory?
No, they're an integral part of the theory, but what's important is that as the theory goes, the mass of a particle is proportional to its coupling to the Higgs. The more strongly coupled it is, the more sort of resistance it experiences as it moves through space, like moving through molasses. And particles like the photon don't couple to the Higgs, which is why they remain massless. But they're still an integral part of the theory.
Yeah, that's exactly right. In a sense, the photon just sort of slips through this molasses, a metaphor I like to use too, whereas the electron feels a little bit of drag and thereby gets a little bit of mass, but a particle like the top quark feels a lot more drag and therefore is a lot heavier. So
the only thing I'd like to say is it's kind of amazing, because if you think about it, that means that everything we see is kind of sort of accidental. At a fundamental level, it's quite different, and we're only here because we have mass, and it's just because of the Higgs field.
Yeah, no, exactly right. So one other final thing, because we're running out of time. Would you prefer that the Higgs particle is found, that today's announcement is correct, or would you rather it be that we rule out this idea that really has been with us for 40 years and send us back to the drawing board?
Well, I'm of two minds. I'm amazed that if it's there, because it's really a theoretical edifice that's been built over 50 years that requires something rather fantastical, this field throughout space, and it seems almost too good to be true. So in that sense, it's amazing if, when you're a theoretical physicist like the two of us, it's weird when you're sitting around at night and you invent something to think that maybe nature accepts that or follows that rule. At the same time, as a scientist, it's almost more exciting to be wrong. And in some sense, if we were wrong, it would indicate there's something fundamentally new. So it's almost more exciting to be wrong. I don't know what you're feeling.
Yeah, I feel the same way in that we love the unexpected. We live for the big surprise. This is not a surprise. We've been, in some sense, anticipating it for 40, 50 years. But to have your math realized in the real world is enormously exciting. You know, I wasn't even born when people started thinking about these ideas, but it's great to see something that I've learned as a student, graduate student, I've taught to students actually apparently coming to life. Certainly from the perspective of convincing funding agencies to continue this line of research, it's better to have something that you can point to than something that is a null result, so we're excited about that. So I think it's an exciting time all around.
It's it's amazing testimony to the power of, in some sense, the human intellect.
Yep. So I will be back in New York in a day or two. I'll post again something that perhaps takes this conversation further. Thanks, Laurence, Krauss, for joining us, and keep sending in your questions.
Thanks.
See you later.